Okay, so today we'll continue shear today. Um, so before we start, just to remind you that the next round of the Zorro Q activities are due on the 14th of October. So just make sure that you finish them all by that date. All labs and all tutorials in this course are optional, so please don't think that you need to come in to attend any lab or tutorial. If you've got any questions, just send me a message or send one of the TAs a message. But everything is optional when it comes to the lab. If you wanted one of these, you can connect them from the technicians in the MDLS. If you've got any problems, just contact them directly and CC me in if you need to. So these are available, and just contact them. And as I said yesterday, you can bring one of these to the exam if you have either printed it or taken one from the university. For the lecture recordings, I've uploaded the lectures for shear as well as buckling onto a high definition YouTube channel. So I've shared the URL with you before. In the last lecture, if you need it or if you can't find it, just send me a link, just send me a Piazza message or send me an email, and I'll send you the link for the page. So I've got one on shear and I've also got one on buckling, and for those of you who want it, I've also added in the LiveScribe videos that were made a few years ago, maybe 5 or 6 years ago, so I know they're out of date. No obligation to watch them, but if you want them, they're there, and they go through some of the examples in this course. So today is the third lecture on shear stress. So as we know, Lucas has spent some time teaching you shear in the last semester. So I would hope that all of the concepts you would already understand. And what we'll do today is to have a look at some of the misconceptions that students have reported in the past. When it comes to doing shear. So let's have a quick look at last year's exam. So last year's exam would be at the back here. So that would be on page 331 of the course book. So there was a question here on shear, so there was a 10-mark question on shear, and if you've done the examples in the course book in terms of the in-class, basic, advanced, exploratory, then you would probably recognize that question anyway, so that you won't have too many shocks when you get to the exam. And sometimes I do have a 5-mark question, which is not worth much, but that would be a pretty difficult question, and that would generally be an exploratory level question. But there's nothing to stop students from getting an A grade if they're not able to do the exploratory level questions. So let's continue here in terms of where we left off. So you've got some problem sheets. So these have been broken up into basic problems. So we've got some basic problems here. You can see this one has been taken from has been reused in a final exam at some stage. You can probably recognize that one has been used in an exam at one stage. This one here is one that can cause a bit of problems, so I'll talk about this one here in this session. Then we move on to the advanced problems. So some more advanced problems here. So this one again, maybe we'll talk about the SSA 8. With a lot of these, the difficulty with a lot of these is just calculating second moment of inertias and first moment of areas. That would be moment of inertias and first moment of areas. So that would just be I, and also calculation of S dash. So you would already have done the basics of that in Civil 210. So I would assume some of you may have some problems, and that's probably not because of the shear, but because of the calculation of I and the first moment of area. So we've got an example here. So this one here, I do remember there was some questions on that one before. It's given the second moment of area of the single section, and then you've got to use the parallel axis theorem at some stage to get the second moment of area of the new section. So it's things like that which can be of concern. And then there's that one there for a wide flange beam. Okay. So after that, there's the exploratory level questions. So if I did have a difficult question in the exam, it would only be worth 5 marks. So you don't really need to worry too much about the exploratory level questions. There's that one there, which is the box section with which has now become an open section, and the calculation for that. That's quite similar to the last in-class question that we talked about. And then we've got these questions here. So for those of you who want them, I think we've provided solutions for those in the Dropbox anyway. So as we move in here, you can see the final exam question has been repeated here from 2018, going backwards back to the 2015 question. And then there's another copy of my of the thing that we did yesterday, where we just folded it to see where the horizontal shear flow came from. So in this part, concepts explained by students. So shear is a funny thing, and it's conceptually a bit difficult until you get the hang of it. So I talked to some students. They put up Piazza questions, and I've just tried to extract what are the most difficult ones. So one of the ones that's a bit difficult is the shear center. So we've got an open C section, which I've drawn there. You can sort of see what they've got there in the experiment is that they've got this going backwards there, and then they've connected something there, which allows the load to be applied. So in one experiment, the load would be applied there. In the other experiment, maybe the load would be applied there. And then in the final experiment, maybe the load would be applied at maybe the centroid. So this sort of experiment, where you're basically just pulling these things down, they're quite useful, because you can see that if you attached a bracket there, which you can see the bracket there, and then you applied the load going down through a bracket, where the bracket goes through the shear center, you would see that when the load is applied at the shear center, there is no twisting or torsion of the section. So at the back of this, all that would be built in. Okay, so we've got a built-in channel section. Apply the bracket, stick a load down, and you can see that when the load is applied down there, the deformed shape, the whole thing would move downwards. So not drawn terribly well, but you can see the concept. When you pull it downwards at that point, the section doesn't undergo any twisting. And as we've said before, there's not much that an open section likes than being twisted. So open sections really hate being twisted. So so that would show physically this concept of the shear center, and I'm sure you can find a lot of YouTube videos about it. So the general concept is you can, if your load or your shear force is applied eccentrically to the web at a position E, which we've got calculations to show how that E is calculated. If it's applied through that position, the section doesn't want to twist. If the load is applied, so let's just leave that there since that shows the position of the shear center. Okay. So if the bracket was slightly longer and if the bracket was there and the load was applied to the left of the shear center, you can see that the section has twisted. So you can see here in the course book that if it's applied to the left of the shear center, that instead of coming down under that action, the section has twisted in that direction, like so. Okay. And then the final example is if the load is applied to the right of the shear center. So if the bracket now is a bit different and the load is applied to the right of the shear center, maybe through that point there, to the right, or in real life the load might actually be applied through the web, since that's where you're putting your screws in, but anywhere to the right of the shear center, and again you pull it downwards with a string. This time the section would rotate in that direction. Okay, so there is this point which is the shear center, and it's not the centroid. The centroid is there. There is this point of the shear center, and if the shear load is applied through the shear center, then as we can see in this example here, where the load is applied through the shear center, the section just deflects downwards and it doesn't wish to twist. So that's a shear center, and if you did Google some YouTube videos, you could probably find something. There's a link down here which you're welcome to click. That's probably where these pictures were taken from, but I think that just physically using a physical model that helps understand what this shear center position is, and then you can work back and do the maths that sort of prove that to you. So this is what the student wrote: shear center application in basic problems. So in order to work out the shear center for a given cross section, we need to work out the dimension and the moment of inertia I. Centroid line position first. Draw the shear flow diagram. So the shear flow, as we said, can either be going this way or this way shown. It doesn't make any difference, and that's because when we've got our simply supported beam under the point load and you take your cut there, and then that you know that the shear force in this side is going down, and we know the shear force in that side is going up. So both of these are the same, they're just on either side of the cut. So don't get confused which way the flow is going. It just depends on whether you're on the left side of the cut or the right hand side of the cut. So we consider the moment equilibrium to find the shear center when the moment caused by the shear forces in the cross section is equalized by the moment caused by the shear force. No torsion or twisting of the beam will be formed. Therefore, the position of the shear center can be calculated. So when the moment caused by, so we've got these forces in the flanges, which these horizontal forces cause a moment. And so when the moment caused by the shear forces in the cross section, particularly with the horizontal forces in the flanges, here and here applying the couple, is equalized by the moment applying the shear force at the shear center, no torsion or twisting of the beam will be formed. So if the load is actually coming down through here, where that distance there is the shear center E, so if the load is being applied through there, obviously there's going to be no moments going through that point, because that's the line of action of that's the line of action which you can see there, so it causes no moment. So this force multiplied by E must be equal and opposite to this couple going in the other direction. In basic problems, the beam cross sections we got are generally not complex. If we got a simple a simple shape, instead of doing a complex integration, we have much simpler methods. For most non-curved cross sections, the shear flow profile can be simplified into combinations of triangles and parabolic shapes. So the shear flow going from this side, so we can call it stress if you like, but flow and stress are pretty much the same. They're just related by the parameter T, which is the thickness of the section. So that would be the distribution of the shear flow going through there, and the area under that becomes the force, or the force acting in the flange. So that's a triangle, and then this side here would of course be a triangle there. And then down here we'll have a parabolic nature with the maximum shear stress being there. So we know from the shear flow that that value of the shear flow Q1, or Q at the corner, must be equal to that, because you, and the reason why it's called flow is because you can think of this as being a pipe and water flowing down, the water flowing down through the system. So work out the shear flow at turning points, so that would be a turning point, and maximum points, and that would be a maximum points. Then work out the area below the shear flow diagram by taking different shape profiles, and that would be much simpler than deriving complex integration formulas. So I don't really like algebra much these days. I just prefer to do everything numerically. So this statement pretty much says in uncomplicated problems it's quite easy just to do it out numerically rather than work out some equation that calculates different things for you. For example, an equation that would find the position of E for a complicated shape like that, as an example. Okay. Taking moment at the members would say has a relatively more complex shear flow profile than other members, would also save a lot of time. For example, this C channel cross section, if taking moment at the web only, forces in the top flanges will be needed for the calculation. Okay. And of course, one of the big assumptions with thin ward, which is, I just like to call it working things around the center line, one of the big assumptions you're making through that is that this flange here this flange here and this flange here don't carry any vertical shear. So if you integrate under here, that would give you this, that VE would be equal to the applied force V. So one of the thin ward assumptions is that your horizontal members, the flanges, are not taking any vertical stresses. So then we come on to this problem here. Calculate the shear center of a horizontal I section. So before we do that one, this is a problem that normally comes up. So if we look back in the course book, the basic question SSB 12, this is one that the students in the past always have some struggle when it comes to shear, and it's probably nothing to do with actually understanding shear. It's probably more to do with calculating second moment of areas and stuff. So I'd like to have a look at that one first. So we have this one. It says calculate and sketch the distribution of shear stress in the monosymmetric I section shown due to the vertical shear force of 1 kilonewton. So calculate and sketch the distribution of shear. So with a monosymmetric section, the shear center is probably, or definitely, because it's symmetrical about that line, unlike the channel section, the shear center will be down along the web. So we can assume that there's, unlike, well, we know unlike a channel section where the shear center is outside, when you've got a symmetrical section, a doubly symmetric section in this case here, the shear center and the centroid are coincident. So it's asking to see, to calculate the distribution of shear stresses. So let's have a look at it. So I use this one to try to explain what the thin wall assumption is. So thin wall is an approximation, so we keep on repeating that it is an approximation. You're saying that there's no vertical shear being carried by the horizontal members, and all the vertical shear is being carried here, and you're saying there's no variation of shear stress along here. So everything effectively has been packed going down these center lines. So it is an approximation. It assumes that the shear stress is constant through the thickness, i.e. there is no increase in shear stress through the thickness. So the shear stress here, the vertical shear stress here, the vertical shear stress here, and the vertical shear stress here in our assumptions are all going to be the same. So there's going to be no variation. And if there's no variation, then why worry about stresses? We can just multiply the whole thing by thickness, and we get something a bit easier, which is the flow Q, than having to think about stresses. So you may not like it. So you may be saying, hey, I've got a very thick section here. I may not like to use the thin wall assumption because I just don't want to. You can always use thick theory, but with thick theory, you're assuming that there is a variation of, well, firstly, you're assuming that the flange shear does carry vertical shear, and secondly, that there is a variation of shear stress along the thickness. So it just makes the calculation effort a lot more tedious. And apart from that, most things in life, you're trying to save material, you're trying to save carbon, you're trying to make things as thin as possible. And as the thickness becomes thinner and thinner, this thin wall assumption becomes more accurate. So here I've just drawn up what I've just said. Shear stresses here, here, and here are the same. The horizontal shear stresses are the same. So why not just multiply the horizontal shear stress by this thickness there and get the flow? And then we're saying that the vertical shear stresses here, here, and here are the same. So if we assume that the shear stress is the same, then it is more convenient to think in terms of shear flow instead of stress, where shear flow is shear stress multiplied by thickness. So we get shear stress in newtons per millimeter squared, or force per length squared, multiplied by the thickness, which is a length, and the units come out as force per length. So it's not a stress, it's a flow, or shear flow, and the units are force per force per unit length, or in this case I like to think in terms of newtons per millimeter. So this is just a dimensional check to show how Q is related to the shear stress. Okay, let's move on. So since thickness is not important for shear flow, we can think in terms of center lines. Please remember again that all calculations are approximations. We have already made approximations. So we're already making approximations, even going back to the engineering theory of bending, sigma equals my over I. That assumes that shear plane sections remain plane. So I've now drawn the dotted line, which is down there. So I've drawn this line here, which it becomes the center lines of the section. So we do calcs around the solid line through here, so let's just make it solid. So just make it solid. So, and the solid line is the center line, okay? So we do our calculations around this solid line. So we've got our top flange, neutral axis, and bottom flange. So let us approximately and so quickly calculate the position of the neutral axis, and let us calculate it relative to AA. So AA goes through the bottom flange. So that just makes our life a bit easier in terms of calculating the neutral axis. But you're more than welcome to take it along that line, or you're more than welcome to take it along that line, or you're more than welcome to take it along that line. So wherever you draw your line, you'll be working out this exactly the same position of the neutral axis. So the position of the NA will work out to be the same. But we do it through this line here because it just saves us one line of calculation, because then I don't need to calculate the area of the bottom line and multiply it by its moment arm. So we calculate it relative to AA, which passes through the center line of the bottom flange. We can put AA anywhere, but if it passes through the center line of the bottom flange, we can ignore the bottom flange in the calculation, saving you very precious examination time. So we want to get the position of Y bar because we are making assumptions, so it's approximate. You can calculate the position of Y bar accurately if you want to, without using thin walled assumptions, but we want to use thin walled because it's faster. So Y bar is the first moment of area of the top flange, so first moment of area of the top flange about AA, plus the first moment of area of the web around AA, plus the first moment of area of the bottom flange around AA, which we already know is going to be 0. And we divide that by the area. So we've got 100 times 10 times 210, plus 200 times 8 times 210 over 2, plus 150 times 110 times 0. This is 0 because we set AA to be coincident with the center line of the bottom flange, so we don't need to calculate it, thus saving time. And I divide that by the area of the whole thing, 100 times 10, 210 times 8, because 8's the thickness there, and 150 times 10 for the bottom flange. And then I get 92.4 millimeters. So using my thin walled assumption, and you're more than welcome not to use thin walled assumption, but then you've got to explain what assumptions you are making. I get my neutral axis to be 92.4 millimeters. So now we find the second moment of area using thin walled assumptions. So I've drawn the solid line here. So the second moment of area about the neutral axis that we've just found is the sum of the second moment of area of the 3 elements. So the 3 elements are top flange, web, and bottom flange using the parallel axis theorem. So here, what is the first moment? What is the moment of inertia of this thing here? So it's meant to be representing what I've just drawn solid. So 1 over 12 times breadth times t cubed. Okay, so we use that equation, and then plus 100, which is the width times t, which gives you the area, times the shift to the neutral axis. So that's around its own axis, and this is the parallel axis theorem bit. So the distance from there to there is 117.6 squared. So area times distance squared. So what is it for this flange, for this web here? 1 over 12 t times the depth, 210 cubed. And then we use the parallel axis theorem. So I'm now shifting it by 12.6, just moving it down 12.6 squared, so we get there. And then here we get 1 over 12 times 100 times t cubed plus 150 times t times 92.4 squared, which is the shift from its own neutral axis to the neutral axis of the section that we've just calculated on the previous page. So I've just calculated it. I've calculated it to be 3309.15. So now let's think about a faster way. Looking at the magnitudes of the 1 over 12 bt cubed. So looking at the magnitude of that, we can see that the magnitude of the 1 over 12 bt cubed turns out to be 0.83, and the magnitude of the parallel axis theorem shift, area times shift squared, turns out to be 382. So this is very small compared with this. And we can see that this is also very small compared with this. So 1.25 compared with 1281 is a very, very small amount. So looking at the magnitudes of the 1 over 12 bt cubed component of the top and bottom flange, we can see that it would not be too wrong to ignore it. So actually, you could have saved some time in your exam just by ignoring having to process the 1 over 12 100 t cubed and that in your calculator. So if we had ignored those, we would have got 3307 times 10 to the 4 compared with the slightly more accurate 3309. And there's only a 0.06% difference between the two numbers. So if you want to spend your exam calculating this, you're more than welcome to. You obviously won't get penalized, but you can see that it may not have much benefit in terms of getting a good answer in a design office. A thin wall assumption, therefore, that the 1 over 12 bt cubed components parallel to the neutral axis line can be ignored, bearing in mind all the other approximations that we have already made in deciding to use thin walled. We have clearly made a lot of approximations in our calculations so far using thin walled assumptions, but let us continue and calculate the vertical shear flow shear stress distribution, because the shear flow and the shear stress is the same, and if the thickness is different between the web and the flange, that obviously means the stresses are going to be different, but the flow is going to be the same. So let's now sketch the shear flow distribution, which we've got there. So we've got the build-up of the shear flow moving from here right to the center line, and we've also got the build-up to the shear flow moving from here to here. So as the student said, why not just calculate that triangle and multiply it by 2? So we'll assume that the vertical shear force is 1 kilonewton. That's from the shear force diagram. So we're just making an assumption because the question didn't say that. Maybe we've got 2 kilonewtons there, so that's 1 kilonewton, that's 1 kilonewton. We're assuming that the vertical shear force is 1 kilonewton because that would be the magnitude of the shear force diagram. Assume that the vertical shear force is 1 kilonewton. Q1 is 1,000 newtons, and you would need to multiply that by S dash divided by I total. So that's done here. So we're taking out this portion here. We're just pretending that we're making our slice, and we can work out what Q1 is just by doing S dash over I total, and we get 356 newtons per millimeter. So that would be the Q1 at that junction there. So I'll just explain how that one was done. We basically have just said that we've got the neutral axis. Here is the flange up there. We've worked out, so we've pretended that we've removed the flange from the section, which will give you the shear flow at that junction, So we've got there, we work out the area, work out the S dash, and divide by I total, and we get 356 newtons per millimeter. So if that Q in the web is 356 newtons per millimeter, then we know that that must have come from the two sides equally. Let's say both the shear flow going in. So both must have contributed an equal amount, which is 356 divided by 2, and then that gives you that value, the 178. So there are other ways to do it, but that seems to be the most obvious one. Q2, so we know that the neutral axis is the position where the shear stress will be largest, and therefore the shear flow. So that would be the neutral axis. So a longer way to do it might be, let's work out that section there. Okay, so down to the neutral axis, and then we've already subtracted it from there. So we'll be working out the first moment of area of that section about the neutral axis, and then dividing it by I. But there's an easier way. The easier way is just to work out what that bit would be. Okay. So if we work out what this bit is, then we already know the value of Q1 at that point. And if we work out the first moment of area of that bit, then whatever the shear flow there is just Q1 plus the bit that we've added. So we can see that here. So at here, Q2, which is at the neutral axis, is equal to Q1, which we've calculated, plus the 1 kilonewton plus S dash over I total. And this time here, we're just taking that portion there because we're going to be adding it onto the Q1. So it's going to be that times 8, which is the thickness, times the same distance over 2, divide by I, and we'll get Q2. And obviously, once you've got your Qs, you can turn that into stresses just by dividing by the thickness. So turn it back into a stress if you want. And then the last one here is Q3, and again, same thing. Let's check this one here. So again, what we've done to work out the Q3 is we'll concentrate on that bit there, and then we'll pretend that the rest of the section disappears, and then that area times that distance would give you the S dash. So that's what's been done here, probably 150 times 10 times 92.4 being that distance, divide by that, and that will give you what your Q3 is. And then from there you can get your tau 3 is. And obviously you've got the 178 at that point there, just divide it by the thickness of the flange, which is 10 millimeters, and then you'll get the stress in the flange, or the horizontal shear stress. So I think I've drawn it out here again in relation to getting the 178, which is just half of the two values, but I hope you get the idea, and maybe you already understood it from what Lucas had taught you in the first semester. So this is the question that I've had a lot of Piazza questions for in the past. Okay. So let's move on. So that brings us on to this question here. So in that question there, which is, I suppose, the 2016 question 2, sketch the shear flow distribution for the cross-section shown. So that should be shown in figure for question 2a. Determine the position of the shear center under the vertical load. Assume that the cross-section is of uniform thickness of 1 millimeter. So everything here is 1 millimeter in this case. So when the section was this way around, then we know that the shear center is going to be down there. But what happens when the section is rotated round? We've now got to calculate the position of the shear center. So go back to what we've already said, is that we've got some load coming down here into the section, and there's going to be some horizontal shear flow maybe, and there's going to be some vertical shear stresses or shear flow. So we know that in the vertical members are going to be taking the vertical stress. So you would expect a parabolic distribution there, and you would expect a parabolic distribution there. And we might maybe say that the shear flow would be going down like there in those two members there. Okay. So once we've got the shear flow, which would be the area under the parabolas, then to work out the position of E, you can find E just by taking moments. So obviously E must be nearer to that side than that side in order for the two to balance out. So let's have a look at the solution. So the thickness is 1 millimeter. So I've got the breadth of the flange and the breadth of the right hand flange. I've calculated I using thin ward. I've assumed the shear load is 1 kilonewton. I've worked out, 1 kilonewton. I've worked out the maximum stress. So I've worked out the maximum stress here, which is 1167. So you can see my calculation there. I've worked out my maximum stress here, which is 666.7 newtons per millimeter squared. You can see that shear and stress are the same. Shear flow and stress are exactly the same in this case, because the thickness is 1 millimeter. So that's why I chose the 1 millimeter. And then you can take moments. Well, firstly, you can integrate under that area to work out the area under the parabola. So there's a rule which you may already know, that the area under a parabola is 2/3 of the stress times the total length, and times T times B. So if you don't know that rule, which you may have covered in geotechnics by now, if you don't know that, you would definitely know it after we've done the virtual work section. So don't worry, but that's how we can get the area under a parabola. And then we can get the area under of the right hand side, which is 0.889 kilonewtons. And then from there you can work out the position of the shear center relative to that side, just by taking moments. So that will give you the position of the shear center. So the student, the former student, who very kindly wrote this out, has provided some notes. The shear flow distribution in the horizontal I section will look like this. We must find the total load in the flanges, and then we use the vertical force to work out where the shear center is. So he's got these. There is zero shear stress in the web, as it passes through the neutral axis, i.e. y0 at all parts along the web is equal to 0. Okay. So I didn't mention here, but you would, since we know that the neutral axis passes through there, if you did want to work out the shear stress here, you would find that it has to be 0 by the mathematics, since the neutral axis passes through it. So to find the force in each, multiply the flange by the parabola. So I think he's got the equation there, and then he can work out the moment relative to each side, and then from there he works out the position of the shear center from the left. So you can see the calculation for that. Okay. So the next problem that students sometimes have is the shear flow in a nail. So when calculating the shear flow, so the nail keeps the the bits of wood acting compositely, so the nail or the adhesive. The nail is responsible for resisting the forces. To keep the section intact, we need to be able to find the shear flow at these specific locations in order to find out the force that each nail will withstand, and then you can work out the spacing. So we've got this question here. So the shearing planes of the nails are as indicated. So here is the shearing plane. So what we're doing is we say we've got these nails here under shear, and these are the shear planes that obviously the nail is under. So what you could do is you could take the neutral axis, take the top plank out, do your calculations for shear flow of the top plank, work out the shear, maybe divide that by 2, and then you've got the force going through the nail. So here you've got the calculation, here work out the flow, and then here I think they're divided by 2 because they're 2 nails, so you didn't have to do it that way. You could have just done it like that, taken half of it. Incidentally, I think you should be able to reason out anyway that the shear flow of a box section, you should have been able to reason out to yourselves anyway that the shear flow of a box section must be going like that. Yeah? So I think I'm sure Lucas would have covered that. So just a bit of thought sort of tells you that that's what you would expect the shear flow to be happening, the vertical members taking the shear, and then these being the horizontal. So we can take that bit out, and if we did our calculation based just on that, then we would get the shear flow acting through the shearing plane of the nail, and then we would be able to work out the spacing. So this question is sometimes asked a different way. So instead of having that section and then you put the vertical section, and then you put the vertical section in, and then you put another horizontal section in, and then that becomes the shearing planes, which we've seen there. What happens if we had 2 bits of solid wood being the vertical ones, and then we've put these here instead, and then we jam a nail through, or jam a nail through. That side. So in this example, this becomes the shearing plane. So that's the shearing plane, and that's the shearing plane. So it's almost the same calculation, but you'll be working off that instead. Yep. And then obviously divide by 2 because you've got 2 shearing planes, so I can see the 2 there, or you can just take half. Okay. And then from there you'll be able to work out the spacing. So that leads on to question 2A from the 2015 exam. So firstly, the related solutions are here for the nail spacing, and also here, so they're in the course book already. So with this one here, what do we do? So we've got our box beam, I'll just draw it like that, and then we've got this bit which has been added, and then you've put a nail through it there, and then there's 2 shearing planes. So how do we do it, or how do we do the calculation? We do it exactly the same as before. Work out the neutral axis of the composite section. Get rid of the box. And just on this bit here, work out S dash for there, divide it by 2, and then we'll get the flow acting through each nail. So the solution for that is here. Okay, so yeah, so it's just a variation on what we've seen as the previous problem. Okay, let's turn the page. And then here the student has worked out the cues, and then from there can work out the spacing. So a student said, essentially what we are saying is that the shear flow at point A can either flow from the upper section to A, flow through the plank, or flow down into the lower section. Because we are concerned about the shear flowing through the plank, we take the first moment of area of the plank. If we care about what's the flow in the upper section, we use the first moment of area of the upper section, and so on for the lower section. So I thought that was quite a nice explanation. So I said thank you for the explanation there. So going on to YouTube, these are some YouTube videos that you can watch, which may give some more visual stuff. So there are 4 YouTube videos that the student from a few years ago identified. If you find some better videos, just flick me an email, please, and I'd be very grateful. And then I'll add it onto the course book for next year. Right. So this one is the basic problem that we well, we didn't quite talk about it here, but why is the first moment of area through the web? I thought if we're looking at the first of the I section, that half a web would have its centroid x distance away from the neutral axis. So I provided an explanation to that question here. Another one, problem sheet J5. So problem sheet J5. Which one is J5? Problem sheet J5. Yeah, so it's that one there. How is the centroid calculated? I don't understand to use the thin walled assumptions. Do we have to use the thin walled theory? And then I said it depends on the question. It may just state to use thin walled assumptions throughout. Please look at the basic questions that I pointed to in class, which is the one that I've just shown. Okay, then that's some comments are left. And then this one is sketch the shear flow distribution for that. Why does this question ask about shear flow, but the answer is just calculate the shear stress anyway? Yeah, and I explained the shear stress and the shear flow are the same because of the 1 millimeter. In this case here. So why is the shear distribution parabolic? And there is no shear flow in the web, and shear distribution is parabolic. You should know this from the first example that we've covered on shear, or Lucas has definitely done that. So you would know from Lucas, even before you started these revision lectures with me, that the shear flow we can prove as being parabolic. And again, if you go back to the YouTube, I've put the shear example 1 here, which shows that it's a parabolic distribution. And 3, look, area under the parabola. Yeah, you can get this by integration. You actually don't need to know that formula with the 2/3 in. You could just get it by integration, which might be much easier, which of course may make you feel a bit more confident in the exam. So shear stress at the interaction of the flange is the web times neutral axis. So again, another question about that. Okay. So so in today's lecture, I've pointed out where things may get a bit confusing. So we're going a bit deeper. So Lucas, of course, explained it very well, but he may not have been demanding that you answer some a bit more complicated questions, as we would find in engineering. And so here I've presented some of the questions that you may be presented with, and they're there for you to go through. And then once you've done that, I think you should be able to answer 2/3 of the exam paper, because we've covered virtual work, and we've covered qualitative analysis, or the David Braun. We've calculated slope deflection, we've now covered the shear and bending. So in the lecture next week, we'll be starting on virtual work. So for the virtual work, virtual work can be applied to beams and trusses, but we're going to be starting off with the truss. So here's a 3D prop that I just got made in the MDLS, which shows a truss. So I thought I might need to color code it, but you can see if I can apply a vertical force there. You could probably see that that member goes into compression. So just pulling it down slightly indicates, because only the compression ones will want to buckle. So that one is clearly in compression, and you could probably feel the tension. So you could probably feel so if you had one of these, you could probably feel which ones of these members are in tension. So that one is in tension, that one would be in tension. So you can actually feel it just by playing. Yeah, so just by playing with it, if it's whether something's in tension or compression. Obviously if you're pulling it down, then if it was a beam, then that would be the tension side and that would be the compression side anyway. But one of the first things to know is how do you identify which one is in tension and which one's in compression. So we look, so if you look through the course notes, which we'll be starting through next week, don't worry too much about the maths, it's not too bad. So that's the truss that I've just shown. So for next week, you will need to be able to know or revise method of sections, method of joints, to be able to work out the forces in each of these truss members. And then the question I normally get is, how do you know whether it's in tension or compression? So just by playing with some examples would help you be able to identify the tension and compression members. So please remember to go through these questions here as a revision before we start on it, because I can't really be explaining how to do method of sections, method of joints. I'm sure you covered it in your first year in the Eng course, and I'm pretty sure that you would have covered it with Quincy and Lucas. So just revise method of sections, method of joints, and I'm pretty sure that they do pop up in the ZORA-Q exercises anyway. So next week we'll start on virtual work. So we'll be going through some of these examples in virtual work. So virtual work is applied both to truss systems as well as beams. Okay, so we'll stop there and see you next week.